anything. That's the only information. When the receiver say, I receive everything up to segment 301, that does not imply that 401 was lost. That does not imply that 401 was lost. It may be that 401 is still in transit, or maybe the receiver received 401, but it does not, it's waiting for a data packet in order to piggyback the acknowledgement, right? Remember, we talked about acknowledgement before. It can piggyback acknowledgement to a data packet, right? So basically, acknowledgement 401 by itself only saying that everything was received up to segment 301. It doesn't say anything about 401 was lost, right? So by sending 4 duplicates, actually 3 duplicates, because send 1 and then 3 duplicates, by sending 3 duplicates acknowledgement, that is equivalent to saying that package 401 was lost. Okay, that was equivalent to saying that 401 was lost. All right. Remember, in TCP, the receiver cannot tell the sender what packet was lost. It can only tell what packet was received, right? Yeah. So by sending 3 duplicates acknowledgement, basically it's telling the receiver 401 was lost. All right. So you can consider 4 acknowledgement as equivalent to a negative acknowledgement. Okay. Joshua has a question. Could you explain how you're welcome, Savash. Could you explain how we calculate the new window size in the quiz? Okay, so we can go over the quiz. Okay, all right, so we can go quickly over it, and then, yeah, let me stop share here. Oh no, it's still this slide. Okay, it's still this slide. Okay, so I think we can share again. So if we go to this example here, all right, this example here, and so the window size is, let's say in this example, the window size is 1400, and a segment size is 200. All right. So when the sender sends 3 segments, basically it has used up 600 bytes, right? Because each is 200 and 3 of them is 600. So from 1400, it uses 600. That means it has 800 left. Okay, it has 800 left here. All right. Okay. Does that answer your question, Joshua? Okay, right. So if you go back to this slide, you can see the scenario for both questions in the quiz. Okay, right. So now we go to ad hoc networks. Okay, we go to ad hoc networks. Right. Let me open the slide. Let me see. Yeah, all right. Yeah, okay, the slide here. Okay, so I borrowed these slides from Professor Workbush and Mishra, okay, from Johns Hopkins University. These slides look very nice, so I just borrowed them instead of writing my own from scratch. Okay. All right. Okay, all right, so So Samyak has a question about the next question. So you can imagine as if this is a credit card, right? Your credit card limit is 1700 and the segment size 300. The receiver accepts 5 segments, right? It's similar to you spend 5 segments of $300 each. So you spend 1500. All right. You spend $1,500 and now you acknowledge the first two segments. Basically, you're paying $600 toward your credit card. Okay, so that means you take 1,700 minus 1,500, which is 200 left, and you add 600 more after you pay off the two segments, right? So now you have 800 left. Okay. All right. Thank you, Paul, for the explanation. Yeah. Right. Okay. Let me go to full screen here. All right. So what is an ad hoc network? So we've seen this before when we learned about introduction to wireless network, right? So we have two types of wireless networks: infrastructure and infrastructureless and infrastructure based. With infrastructure network, we have a fixed wire backbone, and the mobile station communicate directly with an access point or a base station. Okay, and it's suitable for when you have location where you can install access point or base station, right? Such as cellular network or local area networks using Ethernet, for example, using wireless LAN, right? Where you have access point and then where you have a base station. Now, so this is an example of an infrastructure-based network. Okay, so we'll learn about this later. Now, ad hoc networks do not have base stations. They do not have access points, right? That's why you can deploy them very fast, right? So the speed of deployment is an advantage. And you can deploy them easily, right? Because you don't need to dig a hole in order to put the base station in. You don't need to run cable or wires, right? And because of that, you can decrease the dependence on infrastructure. So you can build an ad hoc network quickly and easily, right? And with an ad hoc network is also called infrastructureless network or multi-hop. Okay, multi-hop because they don't have any access point or base station. So every node in the network has to work as router to route packets for other nodes. All right. Sorry. And it could support anytime, anywhere computing. Please excuse me for about a minute. Yeah. All right, I'm very sorry. My sore throat never went away. Okay. All right, so let's continue. So an ad hoc network can support anytime and anywhere computing, because you can build a network very quickly and easily. There are two kinds: heterogeneous, in the sense that different stations have different capabilities. And you can have homogeneous network where all the nodes have identical capability and responsibility, right? Okay, so how do I go to the next slide here? Okay, so this shows how a mobile ad hoc network works. So as you can see, they don't have any infrastructure. So every node has to act as host and router at the same time. And these circles represent the transmission ranges of these nodes. So in order to, let's say, transmit a packet from this node to this node had to work as a router. So we have a path here, right? We have a path here. So in order to connect this with this, the problem here is when they move, right? The term mobile is here. When they move, then the topology will change, right? Because they move around. And you can see now we have this topology here. So basically, we have to re-establish the routing part, the routing path from this node to this node, okay? And obviously, mobility causes route changes. And this is a very difficult, challenging problem in mobile ad hoc networks, how to route packets when the network topology keeps changing, right? So an ad hoc network is a self-organizing and adaptive network. We can build a network, we can remove it spontaneously, quickly and easily. Every mobile node host act as a host and as a router. We support peer-to-peer communication or peer-to-remote communication. It can reduce administrative costs because we don't have to build base station or access point, and we can deploy these networks very easily. Right, so let's see how they operate, all right? So, so this to illustrate the idea of multi-hop communication and a peer-to-peer multi-hop network. So when A wants to communicate with B, if they are within each other transmission range, then a wireless channel is available between them, right? Then they can communicate directly. If this channel is not available, so assume that this link here between A and B does not exist, because, for example, A and B are too far away from each other, right? Or maybe there's an obstacle here, maybe a wall or a hill here. So A and B cannot talk to each other. So in that case, they have to go through D, right? So now D will work as a router between A and B, okay? So in this case, D acts as a router for A and B to communicate, okay? So similarly, if A wants to talk to E, it has to go through D, for example. A wants to talk to C, it had to go to D, E, and C, and go to C. Or if there's a link here, then it goes through A, B, and C, right? Okay, and now how do we start these nodes? So at the beginning, when we just build up the network, let's assume that A and B will join the network first. So both of them will broadcast messages called beacons, right? Or we sometimes in some papers, they call hello messages. Basically, they tell the other nodes in the network about their presence. Basically, they say that I'm here and this is my address, okay? And the address may include, let's say, GPS information, okay? And then by receiving these messages, A and B knows that they exist in the network, so they can communicate with each other using a channel. Similarly, A and D knows that they are within each other transmission range, and B and D, for example. And by exchanging these beacon messages or hello messages, they know about the presence of other nodes in the network, and they can update their routing table to show that if A wants to talk to C, it had to go through B, right, for example. And A wants to talk to E, it had to go through D, for example. All right, so in the previous example, we assume that A and B join the networks first, right? And then C joins the network again, it will send a beacon signal. Now, in this case, the beacon signal or the beacon message will reach B, but it may not reach A, right? Because A and C are too far away from each other. So in this case, B knows that it can communicate directly with C, but A can't, because A may not even hear from C, right? A will not hear from C. So by doing this, every node knows that who is their neighbor, right? Who are their neighbors. By doing these kind of hello messages and beacon messages, they can build a table in which they know who their neighbors are, okay? And then based on this information, they can have they can update the topology, the network topology, and the topology include the address as well as the route, right? For example, B will know about the address of C, and it knows that it had to send packet to C. At the same time, if D and E join the network, they perform the same operation, sending hello messages, beacon messages, and then know about their neighbor, where the neighbor are, and then update the routing information. Okay, all right. Okay, so but one thing we have to keep in mind, once they have the topology may not exist in the next moment, because as long as they move, the topology will change, right? So what it means is they have to periodically send out beacon messages in order to update their neighbors about their current locations, all right? And that is one overhead, a big overhead of mobile ad hoc networks, because nodes are moving, so they have to keep updating the network topology, keep sending out hello messages periodically. Right, so, and this is it showed the process of updating the location and the route. So first, between when C joined the networks, B and C will exchange messages, right, to update topology. And then after after B and C, so first A and B exchange messages to update topology, and then B and C exchange messages to update topology. And then now A and B can talk, and B and C can talk. Okay. Now, as I just mentioned before, if nodes move, that may cause links to be broken, right? And link package breakage requires route updates. Okay. So assume that this link is broken. So in that case, A and C can still communicate by using D and then E and go to C, right? So that means now A has to update its routing table to say that in order to get to C. So basically, when this link is broken, the information will be broadcast. So B will tell A and D that now I no longer have the link to C, all right? So when B tells A and D that I no longer have the link to C, A will update its routing table to remove the entry A, B, C from the routing table. So now A knows that if there is a packet to send to C, it has to go through D, right? Right. So when this link is broken, B and C will update the topology and the routing table. And then B and C will tell A and E about this link. So A and E will update the routing table and the topology. And then after that, D If D can hear from B, then it can update the same time. If not, then A or E will tell D that the topology in the network has changed. Okay. All right, so what are the challenges facing ad hoc network? First, the traffic characteristic may differ in different kind of ad hoc networks. They have different bit rates, they have different delay constraints, different reliability requirements depending on the environment. If the environment has too many obstacles, and we learned before, we would have different kind of losses caused by the environment. The traffic is different between unicast. Unicast is one-to-one, multicast one-to-many, and geocast. Geocast means the routing is done based on location, not based on a graph. When we say location, for example, by GPS location, so it's called geocast in that sense. And there are different kind of addressing. Host-based addressing is what we've been learning so far. We have IP addresses, we have MAC addresses. There's also something called content-based addressing. So in this case, the address is determined by the content, not by IP addresses, not by MAC addresses. It's by content. So if someone wants to access a movie, for example, then that movie is stored in some server. And then the person who requests the movie does not know the address of the server, the exact IP address, but the system will send the request on his or her behalf to the server that has that movie, for example. Capability-based addressing, again, depending on the authorization. So, for example, if a server allows a client to access its server, then it will provide authorization for a limited time. So this capability-based addressing was proposed to avoid denial of service attack in order to limit access to a server, for example, based on authorization. Okay. So based on all of these, you can see that different traffic characteristics. So that makes designing routing algorithms for ad hoc network very difficult. And an ad hoc network may coexist and cooperate with an infrastructure-based network, and integrating these two networks may have several challenges as well. But from now on, we'll only consider ad hoc networks that stand alone without any infrastructure-based network, okay? Because this is a very challenging problem to integrate them, both types of network together. Okay, so they can have different type of traffic profiles. For example, this is bursty traffic, peer-to-peer. This is traffic in a group, so that's why it can last longer. Or this is a hybrid environment where you can have one-to-one traffic or group traffic as well. Different type of traffics. All right, so these are the challenges in a mobile ad hoc network. First, a host is no longer an end system. Now it can act as a router, right? Intermediate node or router. Secondly, the network topology changes over time. As soon as you build a path from a source to destination, nodes will move, and then you would lose that route. Okay, and because nodes are moving, your network may partition, and then now you have two separate networks, and then they may not be able to communicate with each other. Nodes are moving, right? And mobile devices have limited power capacity because they're not plugged into a constant power source. They operate by batteries, and if they run out of batteries, so basically the node fails, and now a path will be broken, right? And obviously wireless bandwidth has limited capacity compared with wide channels. And the channel quality varies as well, depending on the environment. As we said, we would learn before, we can have multi-path propagation, for example, reflection, diffraction, those kind of interference, right? So that makes building a mobile ad hoc networks and designing algorithm very challenging. Okay, so obviously it has to be distributed because there cannot be any centralized entity to operate. You don't have an access point, you don't have a base station that acts as a centralized entity, right? And we have to consider how to support routing, how to support channel access, and how to deal with mobility, right? How to minimize power consumption, how to use bandwidth efficiently, okay? All right, so in terms of routing, so we'll talk about routing first, and then we go to a routing algorithm, which is dynamic source routing, okay? So routers are now moving. Basically, every node is moving, and they act as routers, so routers are moving. And then because when routers move, when nodes move, you lose routing paths. So you may lose packets, right? And then you may have to retransmit packets as well. So that's one problem. Lost packets, high packet loss rate. Another problem is a lot of overhead because every time nodes move out the way we talked about before, they have to send message to tell their neighbors about the changes in topology so that the neighbors can update the topology and update routing table. So event updates are often sent, and this causes a lot of overhead in the network. Routing tables may not be able to converge. They may not be able to stabilize because as soon as you have a routing table and then nodes move, right? And when nodes move, the routes will move. And then you have to update the routing tables. And as soon as you update the routing tables, they move again. All right, so they may not be able to stabilize or converge. And routing loops may exist as well because now we don't have a deterministic topology. You may build one route and then the next route may form a loop with the previous route. Okay. So current wired routing protocols that we've seen before, like open shortest path first, using Dijkstra algorithm or Bellman-Ford algorithm, they use shortest path metric. These cannot be used in mobile ad hoc networks anymore because now the link costs will change over time, right? Because as they move longer, the delay, they move longer from each other, you have to reduce the transmission rate. They move closer, you can increase the transmission rates, right? And as soon as you have a shortest path, they move out the way the path is no longer the shortest path, even though it's still there, but it's no longer the shortest path. So how do we solve this problem? So that's why we cannot use the routing matrix that we use in the wired network. Okay. All right, so now we can stop here. We talk about routing and we come back about these challenges later when we go to the issue of channel access. Okay, so let's go to the first routing protocol, which is, so before we go into that, I just want to talk a bit about mobility. So when nodes move, that will affect the signal transmission, right? So it will affect communication. Remember we said before, the longer the distance between any two nodes, the lower the transmission rate, right? We said about that before. So that's one change. As nodes move far away from each other, as they move close to each other, they may use a higher transmission rate, right? How do we adjust for that? Okay. Mobility will affect channel access. Basically, will affect medium access control. And obviously that will affect medium access control for sure, because now you have more nodes interfere or less nodes interfere, right? It affects routing because it will change the routing path. It will change the, it will cause packet losses, right? It affects multicasting, affect one-to-many communication, and affect application as well. So if you have a, let's say a video, a streaming video, if you lose too many packets, the quality will suffer, right? Okay, so there's a question from Samia. In ad hoc communication, we don't use any wide station. No, we don't use any wide stations. No, we only use devices, and they act both as a host and a router, and they use wireless communication between them, and the communication can be multi-hop wireless communications. There's no wire networks in this case. All right. Okay. Now the only exception is, for example, let me give one example here. Let me go back to this example. All right, so let's say, let me try to, okay, so let's say, assume this is, okay, assume we have this network, right? And assume this is a battlefield, right? A battlefield. So this is in a military application. So obviously, these communication stations only talk to each other. Okay, they talk to each other, so that's fine. They basically, this is an isolated network. But if you have an application like this, for example, and these devices want to talk to the internet, right? To the internet, then this station may be connected to, let's say, a base station. And from the base station, it will go into the internet. That's where you can have the wide connection from this part, basically the base station and the internet, right? But the ad hoc network itself, it doesn't have any wire, right? It doesn't have any infrastructure. It doesn't have any base station or access points, okay? All right, any question about this? Okay, so not, then we go to dynamic source routing. So a few things to keep in mind before we go into dynamic source routing. The first thing here is mobility will cause many problems, right? It will affect routing, okay? Because routers are moving. So we'll lose routes. Even after we build a route, we may lose it when a node moves. We may lose packets. There will be a lot of overhead in order to update a route, right? Routing table may not be able to stabilize, and routing loop may exist, all right? Okay, so we have to keep these problems in mind when we design routing algorithms for ad hoc networks. Okay, a question from Joshua. Do ad hoc network not try to reduce the number of hops? Okay, reduce the number of hops. No, that's not a routing criterion. That's not a routing criterion, because how can you reduce the number of hops when you don't have the network topology? You don't have a stable network topology, right? You can, at this instant, let's say at time 4:30, I have the topology. I can try to build a path with the minimum hop from a source to destination. And then at 4:05, some nodes move. That path may not be the shortest path anymore, right? And basically what I did before, spending a lot of time and energy to find the shortest path, is wasted, because nodes are moving, node moves, and then I don't have the shortest path anymore. Why would I waste my time and energy doing that? All right. Next question, station use whatever route they find first forward. Exactly. So that basically they are in the survival mode, right? You can think about that in the survival mode. They just use whatever route they can find first in order to route packets, okay? And we'll see that with dynamic source routing, all right? Does that answer your question, Joshua? Okay, yeah, that's a very good question in that sense, because now we cannot use shortest path routing anymore. And yes, we have to grab whatever we can, whatever route we can in order to transmit packets, yes. Okay, so let's go to dynamic source routing. Okay. Yeah, so that's one issue with mobile ad hoc networks. You should not think about optimization, because as soon as you think about optimization, you optimize something, the next minute, it may become useless, because nodes will move, right? And you lose that kind of optimization. Okay, source routing. Okay, so again, I borrow these slides from these professors. And this is the textbook. But you don't need to read this textbook. I think I already posted a description of DSR and ODB on eClass, and you can find many, like papers or web pages that talk about DSR. This is a very popular protocol for mobile ad hoc networks. All right, so these are the, so the term is dynamic source routing, okay? So the first point is it's reactive or on demand, okay? On demand or reactive means we don't build a path from the beginning. We only build a route when we need to send a packet from a source to destination, all right? So you can imagine if you have an ad hoc network and no one wants to send anything to anyone, there's no transmission in the network. Basically, you have no routing tables in the network, okay? No routing information in the network if no one wants to send anything to anyone. So this is different from the internet, right? When we talk about routing on the internet, we have the open shortest path first. With the internet, as soon as you start the network, you initialize the network, every router will have the network topology, and every router will compute the path to every other node in the network, right? So even if no one in the network sends anything to anyone, you still have those routing tables at every router, okay? This is different in DSR. Routing paths are built only when a source wants to send data to a destination, okay? All right, and it's developed at CMU, Carnegie Mellon University in 1996. And when a source wants to send data to a destination, it will start a process called route discovery in order to find a path from the source to destination. And this is done on demand only when needed. And then there's a process, a procedure to maintain these routes, right? We want to maintain this active route so that the source can keep sending data to the destination. Now, there is no periodic activity of any kind to maintain the routes. So in AODB, there are something called hello messages in order to maintain the routes, but there's no maintenance, no periodic activity in DSR. So we'll see that later. And DSR uses something called source routing, okay? Source routing means it doesn't use a routing table. Instead, the entire route is stored in the packet header, all right, in the packet header. And every node that receives the packet will look at the header to know the next node in order to forward the packet to the next node, all right? It's called source routing. It's different from routing using a table. With a table, you don't care about the source or destination. You take a look at the routing table. You know that in order to send to the next node, to that destination, you have to send to the next node using the routing table. Here, the entire route is stored in the header, okay? So you can imagine this as GPS information, right? You store entire route on your phone, right? And the GPS will tell you what to go at every point on the road. And it uses caches to store routes, okay? And we'll talk about caches later to help to optimize network performance. And it can support unidirectional links. That means you can have a path from A to B and a different path from B to A as well. If you don't have bidirectional links, right? You can have a path from A to B, another path from B to A, okay? But for now, we assume that the network has bidirectional links. And in that sense, if you have a path from A to B, then the same path is used for communication between B and A, all right? So for now, we assume we have bidirectional links. If we have a path from A to B, the same path can be used for communication from B to A. Okay. All right. So again, no routing tables, right? So when a source wants to send a packet to a destination and it does not know a route to the destination, it will initiate a process called route discovery. Okay. So S will flood the network with a route request, okay, route request, and I mean the abbreviation is RREQ. Okay, so the keyword here is flood, all right. So we'll see why later it's called flood. We don't call send, we don't say transmit, we don't say send, we say flood, and you see later why we call it flood. Okay, so this is one important point to remember. And then each in a route request, it contains the sender address for sure, right? The destination address for sure in order to find the path from the sender to destination, and a unique request ID determined by the sender. Basically, this is the ID of the message, all right? And of course, every request must have a different ID, okay, to avoid confusion. And then when an intermediate node forward the route request, before it forwards the route request, it will append its own identifier or its own address into that route request. Okay, so we'll see it later. Okay, so let's consider the route discovery example. Okay, so in this case, S wants to send a data packet to D, right? But it doesn't have a route to D yet. So what it does is it broadcasts a route request, okay? And in this route request, there would be S, and then obviously there will be the address of D in here as well, and a unique request ID, but we don't show that information here, right? Okay, so the term here is broadcast, okay? So basically it had to broadcast so that this request can reach everyone. And that goes back to the idea that it just tried to find whatever route it can find to route the packet from S to D. Okay. Right, so it broadcasts the route request. Now A will receive the route request, but it does not have a route to D, right? A may have a route to D. If A has a route to D, it will reply to S with the route, so it can save time. So we'll talk about this later using a cache. But in this case, assume that A doesn't have any route to D. So if A doesn't have any route to D, what it does is it will add its own address to this route request. Okay, it will add its own address to this route request. So you can see by adding its own address to the route request here, it will mark the path that the route request takes in order to go from S to D. All right, you can think of it as like a breadcrumb to mark every node that the route request has to traverse. And A will add its own address to this route request here. So now we will have SA, right? And then it broadcasts the packet to everyone, right? Again, the operation is broadcasting, okay? And when A broadcasts that, obviously B and C will receive the packet, right? It will receive the packet. Okay, so the message. Okay, so we'll talk about that already. So let me see here. So this is from the D point of view. Okay. All right, so now this is from B and C point of view, and then we go back. This is for D. So B and C receive the message from A, right? When B or C receive the message from A, B and C does the same thing as A. If it has not seen this message before, right? If it has not seen this message before, or it has not seen or has not done anything with this message before, then it will add its own address to the route record, and then it broadcasts the message again to the next hop neighbors, to everyone else around it. Okay. Now, if it's already seen this message before, or it has already added this address to the route record before, that means now it's received a duplicate message. So in that case, it just ignore the message, right? Throw it away. So in this case, in this example, B will add its own address here. So you would have SAB, and then C will add its own address to this. So you will have S, A, and C, right? So, and then B and C will broadcast to everyone. Okay, so B and C will broadcast. Now, if B broadcasts the message to everyone, so assume that A and C receive the broadcast message from B. A will see that its own address is already in here, SAB. So it will ignore the broadcast message is received from B. C receives the message from B. It will check the request ID and it say, oh, I already have this request ID. I already seen this request ID from S. So that means this is a duplicate message. So I just ignore it. So B and C will ignore it, right? Yeah. So in that sense, when B and C ignores the duplicate message, sorry, A ignore duplicate message, C ignore the duplicate message, it saves the network bandwidth instead of relay those messages again. Okay. So now we at this point where C will broadcast the message with SAC, right? So the message with SAC will reach D, okay? And this is the action that D will take here, okay? All right. So now D will look at the route request and it see that it is a destination, right? So it knows that it have to do something. So it will create a new message called route reply, okay? Route reply. And then it will, remember we have SAC, right? Now D will add its own address to that route. Now SACD. It will copy SACD from route request to route reply, okay? And then it will send this route reply back to the sender, to S, okay? It will send the route reply back to S. Now, okay, you can see that at this point, the route reply has SACD, right? So D will send the route reply back to C because C is on the path. C looks at the route reply SACD. So C knows that it had to send to A, right? So it sent to A. A received the route reply and A sees SACD. So A knows that it had to send the route reply back to S. And that's how the route reply goes from the destination D back to S, all right? And remember, this is unicast one-to-one because now we have the route in the route reply, right? The route reply contains SACD, okay? So now it's unicast, it's not broadcast. The route request have to be broadcast because we don't have the route yet, okay? All right, any question about that? Okay, so that's how the route discovery process is done, right? So we've said about this, we have S and then arrive, broadcast to A will attach SA and then send to B, broadcast again, B and C receive this, and then C will add its own address, SAC. B would do the same thing as well. B would do SAB as well, right? But we don't see it here. But B would have to do the same thing. It broadcasts SAB, okay? But that message will be ignored by A and ignored by C. Okay, and then it's arrived at D, right, SAC. And then at this point, D will add SACD, right, at D tier. So now SACD, and it sent back SACD back to C, to A, and to S, the route reply. Okay. All right. Any question about this? Okay. So the concept is easy to understand, right? Okay. So this is talking about links that are not bidirectional, okay? Because the route reply, if links are not bidirectional, then the route reply may not be able to take the same path back to S. Okay, so in this example, we assume that our links are bidirectional. Okay, all right. Okay. So yeah, so this is like additional information to know if the link are not unidirectional. So in that case, the route reply will take a different path from the route request. Okay? So, but to make things simple, we assume that we have bidirectional links. Okay, so the route reply should have SACD, right? It should have SACD. Okay. Here. Oops, sorry. Okay, because of my dog, just 1 second. Let's wait for her to stop barking. Oh my gosh. Is she that loud? Okay. Sorry, 1 second. Let me go down and make sure that she doesn't. Sorry about this. Yeah. Okay. I'm sorry. Okay, I'm sorry. It's like I said, it's very hard to work from home with a dog. All right, at least it's not a baby. Yeah. Okay, so let's continue. Okay, all right. So again, just to repeat, D will copy the whole path, the whole route into the route reply and send back to C. C will look up at the route reply, the path sent to A, and then A sent to S. Okay. All right. Yeah. So this is the process here. Okay. Right. Okay. So that is one example. So we have one more example here. Okay. So we'll go through it very quickly. There's a question: when a route reply is received, a node uses the route request to determine which node to unicast the route reply to? No, like I said here, I think because the slide may be confusing. When D send back the route reply, remember there's a slide here, it says here, let me get it. Okay, the destination copies the accumulated route record from the request into the reply. Okay. Yes, the route reply contains the whole path to the sender. Yes, it copies the accumulated route record from request to the reply. Okay, and that's how every node on that path knows where to send the route reply back to the sender. All right. Okay, let's see here. Let me go back. Okay, so this is one example. So we'll go through it very quickly. One more example to understand the concept here. So S here, destination here, right? S will broadcast a route request. When S broadcasts a route request, so basically B, C, and E will receive it, right? Yeah. Oh, so that's where the term flooding comes from. We talked about before. Because every node receives it. If this has not seen that node before, that request before, it will broadcast to everyone else. So basically, you will have a flood of route requests in the network. All right, so that's why the term is flooding. Basically, broadcasting. The whole network will be flooded with these route requests. Okay. So S will create a route request, put its address in there, and then broadcast to everyone. Okay, one more thing to keep in mind, these links, these lines, these edges, they're not real, right? They are wireless links, okay? So that they represent the transmission range between E and F, right? For example, between C and F, there's no transmission range, but they're not real links, right? They're just wireless links, yeah. Okay, and then now B, C, E receive, right? On three of them have not seen these before, so they will broadcast to everyone else in the network. So B will broadcast to A and H, C broadcast to H and G, E broadcast to C and then F, and then yeah, E then F. Okay. All right. So a question from Samia: nodes and their addresses. Add the addresses to route reply or route request to route request. Note that add the addresses to route request, not to route reply. Okay. All right. So so you can see there are 2 points to mention here. H, both B and C will broadcast the route requests, right? And that's why these messages may collide at H here. Okay, so there may be a lot of collision in this case at H here, all right? They may collide here, so that's one point. The second point here is you see that when E broadcasts the route request, C will receive the route request as well, right? Because they are within transmission range of each other. But when C receives the route request from E, it will take a look at the sender and sender ID and address, and it looks at the request ID. So it determines that the request from E is a duplicate request. So it will throw away that duplicate request. Okay. So there are 2 points to remember here: potential collision, photo collision, and how C or any other nodes may receive duplicate requests by examining the sender address and the request ID and determine that this is a duplicate request and throw the request away. Okay, the second one, the duplicate away. Okay, so how route reply has whole path if addresses were added to route request and not to route reply. Okay, I see it's here, Samyak. The destination, sorry, I chose the wrong one. Okay. All right, how do I highlight in here? Sorry. The destination, okay, copies the accumulated route record from route request to route reply. Does that answer your question, Samyak? Okay. Right, okay, so let's get back to this. All right, so 2 points to remember here, right? Potential for collision and duplicate requests will be thrown away. Okay, now here C will broadcast to G. So we'll come back later if the route is not bidirectional, Abdul. Okay, we'll come back later. Okay. So I just want to continue with bidirectional links to avoid any confusion, okay? Because if we're talking about two things, so people may be confused there. Yeah. Okay, so I'll keep that later. All right. Okay, so E will broadcast. E will add its own address to the route request and broadcast. The same with C, add its own address and broadcast. Now, remember, A and H would do the same thing as well. It would add its own address and then broadcast as well, but we don't show it here because that would be too much information here. But A and H would do the same thing as well. It would have SA and then broadcast and SH and then broadcast as well. Yeah. Oh, sorry. Let's say SB here, right? And then H receive, that would have SBH and then broadcast again, but we don't show the information here. Okay. Right. So next. Okay. Again, we have the broadcast message from E arrives at F. F its own address here. SEF. And G received from C, it will ask G here and then broadcast to everyone. Now again, you can, like I said before, you can have a message SBH from H, SBA from A, but we don't show it here. You can also have SBHI from I as well, right? But we don't show it here, okay? Yeah, we just keep two important paths here, but there can be many other route requests duplicated throughout the network and flooded throughout the network. Then, all right, so this will arrive at J. So we have SCFJ, and that this arrive at K. So we have SCGK, right? And then again, there may be others as well. We just don't show them here. And then this can be forwarded to M. And then M to L, but that is the dead end, right? But there will be one that will arrive at D here, okay? That there will be one, either this one from here or this one from J or this one from K, that will arrive at D. So let's see which one here. Okay, all right. So basically this one wins, right? The request from J wins. It arrived at D first, okay? So D will copy the whole path, S, E, F, J, D, right? And then, or D, J, F, E, S, it will copy in the reverse order into the route reply and send to J, J send to F, F send to E, and then E send to S, all right? And when this route reply arrive here, S will have the path from S to D, okay? Now, if this if this request arrives at D, D will throw it away, right? Because it will see that, oh, I already sent back a route reply. I've seen this request before, I send back a route reply, so D will ignore this message, okay? Right, so, all right, so how data is delivered using DSR? So when S receives the route reply, it knows the path from itself to D. So it will store this path S, E, F, J, D. Okay, it will stop. It will store the this path in its let's say it has a cache. It will store this path in there. when it has data to send, it will copy the path to the data packet, right? So everything will be copied to the data packet. Everything will be copied here. And then the data packet will be sent from S to E. E takes a look at the header and see the path. So from E, it had to send to F, so it's sent to F. F takes a look at the header, knows that it had to send to J, and then J has to send to D. Okay, send to D. All right. Okay, so and that's how data is sent from S to D. Okay, and that's the process of route discovery and data delivery in DSR. Okay, there's a question from Samyak. How do we know when to stop the broadcasting? So when, let's say, when do we know to stop broadcasting? So it will go in waves, right? It will go in waves. So when it arrives at D, anything else from D will be, I mean, if D receive anything else, the duplicate, it will ignore it, right? So at some point, every node will receive a duplicate. And when it detects a duplicate, it just ignore that message, and that's it. Everyone will stop broadcasting because it will ignore the duplicate, right? So the broadcasting will be stopped when every node in the process receives a duplicate. And when it's received a duplicate, it knows that it can stop sending. And that's how the flood or the wave is stopped. Okay, does that answer your question, Samyak? Yeah, okay. All right, so I think we can stop here with DSR, and we continue DSR after the reading week. All right, so the lecture officially ends here. Next week is a reading week. No lecture, no lab, but TA will have office hour on Wednesday. I have office hours by appointment, so please send me an email and I'll let you know the exact time and date. Okay. Otherwise, have a nice long weekend. Have a nice reading week. Good luck with your midterm test, and I'll see you after the reading week. Okay. Or tomorrow, I still have office hour. All right. And I'll stay for about 5 minutes if you have questions. Okay. Right. So. Okay, and this syllabus for the midterm. Okay, so the midterm will be everything from the beginning up to, I will post more information about the midterm later, but everything from the beginning and up to the lecture on, let me check, on November 3rd. Okay, November 3rd. That means everything from the beginning up to the lecture after the reading week. Okay. Tomorrow, my office hour is from 1 p.m. to 2 p.m. Tomorrow, my office hours is 1 p.m. to 2 p.m. Okay. Okay, all right. So I will explain about accepting and acknowledging. Okay, all right. So let me open a slide. It's easier to write on the slide. Yeah, 1 second. Okay, let me slide. Okay, new slide. Okay. Okay, I'll share the slide. Okay, so I don't remember the exact number. I think the window size is 1700, right? The segment size is 300. And then received 5, right? Receive 5 and acknowledge 2, right? Okay, acknowledge 2. Okay, all right. Is that your question that you want to discuss, Joshua? Okay. All right. So, so you can think of this as your credit card, right? If the segment size is 300 bytes, then if you receive 5 segments, right? So that would be equal to 1500 octets, right? Or bytes, right? Okay, now, so when you, at the beginning, you have 1700 bytes as a credit. If you receive 1500 bytes, okay, what it means here is, now imagine as if you have a credit card with a limit of 1700 and you spend 1500, right? You spend 1500. So how much do you have left on your credit card? So that's a question for Joshua. I hope you have a credit card. Exactly. Right. Now you have 200 left, right? Why? Because you have 1700, right? And you spend 1500. And now you have 200 left. Okay. Now, when a segment is acknowledged, that's equivalent as you pay back the money you own to the credit card company. All right. If you have 2 segments, what it means is you pay back 600 bytes, right? Or $600, right? Okay. Now, if at this moment your credit is 200 and then you pay back 600, that means you have another increase of 600, right? In your credit because you pay back $600. So what is your new credit on your credit card? 800, exactly. So that is the new window size. That means you can send 800 bytes without receiving acknowledgement. Okay, you can send 800 without receiving acknowledgement. Okay, so does that answer your question? Okay, so when a receiver acknowledges, it can accept more segment. Exactly. So when it acknowledges, that means now it can free the buffer, right? Because it knows that the data has been received correctly. So it acknowledges and free the buffer. And by freeing the buffer, it can receive more data. Okay, you're welcome. So it's the same concept if you think from a sender point of view as well. Okay. So let's say this, if you think about this from the sender point of view, it's the same thing. Instead of receive, now it could be send, right? Send, yeah, send 5 segments, right? And instead of acknowledging, it received acknowledgement, right? Receive acknowledgement for 2 segments. It's the same concept as well. Okay, so when it sends 5 segments, the credit is reduced to 200. And when it receives acknowledgement to 2 segments, it can get back 600 bytes in credit. So now the window size is 800. Okay, it's like this a symmetric calculation. Instead of receiving, not sending. Instead of sending acknowledgement, now receive acknowledgement. Okay. Anyone has a question? I heard someone talking. Oh, 1 second. Yeah, sorry. Let me. All right. Okay. Yes, please. Okay, let me stop sharing here and then I'll get the TCP slide. All right, page 10. Yes, okay, we got it here. Yes. Oh, you want to share? Okay, 1 second. Yeah, so let me stop sharing, then you can share. 1 second. Let me. Okay. Yes, you can share now. Mm-hmm. 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 Exactly. Yes. Yes. It's the same. Exactly. Yes. Yeah. It's the same. It's the same concept. Yes. Yeah. Yeah. No, it's not that part. It's not under there. It's up some here. Let me think again. Sorry. Can you make it bigger? Uh, mm. You know what? Let me share the screen. Yeah. Yeah. Sorry. Just 1 second. Let me take a. Yeah, just 1 minute, please. Yeah, sorry about that. So I answered Joshua's question first. So on Tuesday, March the 1st, I will not repeat the whole lecture. Basically, I will, in the lecture, if you have questions specifically about a topic, so I will explain only that topic, but will not repeat everything. All right. Yeah, and then of course you can ask any question you want about the lecture as well. Yeah, exactly. Does that answer your question, Joshua? So yeah, basically I will not repeat the whole lectures, but only focus on the topics that people want to know more about or need more explanation. Okay. All right. So let me see here. That would be from the sender point of view. That would be similar to let me see here. From here to here, right? Yeah. Yeah. Right, from here to here. So send here. This is a window, send 3 segments. So you have 800, let me see, 800 left, right? 800 left, and then this will be acknowledged up to 1600. But before this point, it will be, it will send 2 more, right? So it will shrink from 800 to only it has only 400 left, right? And then when it receives acknowledgement here, it can extend up to maximum of 1000. Yeah, so it would be this part here, okay, from the sender point of view. Yeah, yeah. You're welcome. All right, so any more questions? So if there's no more question, then so have a nice long weekend, everyone. And I'll see you tomorrow or next week. All right. Okay, bye for now. You're welcome, Samia. Bye.